All right. Okay. I think we should be live right now. So if anyone's on the stream, just say hi. All right. So hoping this stream can be, the smallest one that I'll ever do, because it's actually pretty, at least the content is not, there's not a lot to cover. So I guess be able to cover this pretty small amount of time. Okay. All right. So I think there are folks just joining in. Yeah, I think I can get started because this is anyway being recorded. We watch it on demand as well. So today's topic is exception handling in ARMv8-A. So we've, in the previous streams, we've covered Cortex-M architectures from ARM. Now we've been working quite a bit with the Cortex-A architecture. So I just thought I'll do a quick stream on exception handling in the Cortex-A architecture. And this is a little different from Cortex-M, where, it's not that different. Still have the same concept of, a vector table, etc. But it's a little different in the way you actually implement it. So we'll go through a couple of those things. So what are we going to be covering today? We'll basically cover this. In the ARMv8-A world, what types of exceptions exist? So effectively, there are 4 types. And then there are multiple exception levels. So you can have 4 into 4, about 16 different types of exceptions. And there's something called the VBAR register, called the vector base address register. And we'll also look at how you actually wire everything up. That is setting up the exception handlers. And also when you actually want to test whether your exception handling logic is actually working, how do you do that? So let's get started. Let's first take a look at types of exceptions in ARMv8-A. So pretty much all of my understanding, and not all of it, but a large part of my understanding started with this particular repo. Now this is, sort of owned by Rust Embedded, but Andre Richter, I think we've sort of spoken about him in the previous streams as well. Ever since we started working on ARMv8-A. So he's actually put together a wonderful repo on using the Raspberry Pi as the demonstration board, and basically put a bunch of OS tutorials together. And there's a particular section in this called, what's that? Yeah, it's chapter 11. It's the foundation for, exceptions that he talks about. Pretty much all of the code that, exists in my repo is also from here, except that I've adapted it specifically for the project that we are working on. But in general, this is how ARMv8-A exception handling works. And since this is a tutorial by itself, I don't have to write anything. Now, I don't have to put any slides together. It already exists and it's wonderfully written. So I highly recommend this repo. Okay, so without any further ado, let me just get started. So as I said, there are 4 different types of exceptions in ARMv8-A. They're listed over here. So when I keep saying ARMv8-A, mostly I'm talking about ARM 64-bit or ARCH 64-bit. All right, and these 4 exceptions are, they're different, based on, what they are for, in the sense, one's called synchronous, the other one is interrupt request. This is what most of us are familiar with. And then there's fast interrupt request, which is basically, a faster version of interrupt request. And then there's system error. So synchronous is basically a type of exception where, first off, exceptions are, simplest way to explain them is when something happens during your program execution, something that you didn't intend, or basically what you didn't intend to happen, not part of your code, something happened, you'd like to handle that situation. And that's predominantly where exceptions come into the picture. And that's, and then the hardware also provides certain options to deal with exceptions. And this is what we're looking at in ARMv8. Okay. So first off, before I go forward, let me just check any sort of, confusion on what an exception is. Yeah, I'll just take a pause because that's important. Because I noticed that, a lot of times the word exception itself might be a little, iffy. What does it exactly mean and where does it sort of pop out? Basically, think about, something that you as the programmer didn't intend to happen and it happened. That's basically when you think, okay, that's an exception. We need to handle that exception, right? And how we handle that, we have a bunch of different. First of all, what are the sources of those exceptions? Where do they? What are the different ways in which we can end up in an exception scenario? Is what we look at, right? So, any sort of confusions on that? Okay, I'm guessing it should be pretty straightforward because we've dealt with Cortex-M. We kept calling them exception vectors, same word anyway. So, or rather handlers, which is the same thing anyway. All right, so if you look at the ARMv8-A architecture, there's the synchronous exception, which basically means your code was executing and it came across your code, that is, came across some particular instruction, or you tried to access something, some part of your, some memory address that you shouldn't be accessing because it probably doesn't exist, or there's some problem with it, etc. That's a synchronous exception because while your code is executing, it has come across something. So it's, in sync with the execution flow. So that's a synchronous exception. The interrupt is basically where what you'd think of as anything that's not synchronous, right? You, as the example is given over here, you basically set up a timer. And then when that timer expires, it asserts the interrupt line. And that's when, you basically know, okay, the timer is expired. So all of that is usually asynchronous. And then there's a faster version of this, which we don't need to cover because we're talking about basics right now. But yeah, you want real fast interrupt processing, you probably use fast interrupt request. The last one is system error. System errors are also pretty much very similar to interrupt requests. They're mostly focused on sort of dealing with fatal errors. Like when you want to know something really bad went wrong with the system, it's going to basically crash the entire system. Signals pertaining to that fall into this category. There's an example over here. For example, if a transaction timeouts on the SOC interconnect. So an SOC is the system on chip. There's a bunch of different components in there. And then maybe there are two different entities or two different things that are within that SOC that are trying to talk to each other, and that sort of timed out. So if it times out for whatever reason, then maybe the system isn't functioning properly, so it might just crash. And these things can be very, very implementation or vendor specific, depending on who's implementing the chip, right? So this stuff, the system error stuff, is very, you will have to keep referring to the manual to figure out exactly what's going on whenever we're dealing with system errors. All right. That makes sense. Like, that's fairly simple, right? Now, the interesting thing is, what I wanted to cover today was primarily the implementation aspect, which is what is the vector-based address register and how do we set up exception handlers in ARMv8-A? How do we test them, right? And I'll show you a demonstration as well. Hopefully we should be able to wrap this up in just a couple of minutes. So, so the way it works is, let me actually give you the high-level view so that you have a mental picture before I just dive into all the details of it. So here is the implementation. Okay, we have our Rust boot project, which is pretty much the place where all of this is happening. So let's take a look at the hardware abstraction layer, which is in HAL. So a quick question before I jump into this and keep moving. Can everyone see my screen properly? There's no issue with that, right? Everyone see my screen? There's no, right? I'm sharing my cool. All right, yeah, there's no problem then. Okay, so in the hardware abstraction layer, so pretty much when we talk about exception handling, it is very architecture specific. So this is ARMv8-A, which is what I've been mentioning. So, but yeah, the way Rust boot's laid out is a little different. We lay it out per board rather than architecture and then per board. We actually say per board, that's it. So if you go into the hardware abstraction layer for the NXP board, which is the one that we are working on, and you look at the hardware abstraction layer in there, you'll find that there's a particular folder called exception. Exception, basically it's called exceptions. And then if I just sort of make this a little bigger, you will see that there's about a bunch of modules in there. The important thing over here is, let's take a look at the exception.s module, you can say. Exception.s is not a module, it's actually an assembly file that we've written by hand. Most of this is from the Raspberry Pi tutorial. So this is just to give you an example. So in simple terms, how does exception handling work in ARMv8-A? You have these, let me just highlight this. These 5, sort of bullet points are exactly how exception handling works. Of course, there's a little more when you start delving into corner cases and a little more complicated scenarios. But this is what exception handling is. That's why it's, it should be fairly straightforward to understand this in ARMv8-A. Whenever there's an exception, all right? Whenever there's an exception, the exception basically jumps to what is called the exception vector table. That's where the VBAR comes in. So there's a particular address, there's a particular register called the vector-based address register. That register holds an address, and that address does not point to a bunch of function pointers saying, okay, you can go there and check which pointer to jump to from there. No, what happens over there is it actually points to the actual implementation of each exception handler. So whenever an exception occurs, the processor will move to the will basically look at the exception. It'll basically pick up the go look at the vector-based address register, and then at the vector-based address register, all your handlers exist, and they are laid out in memory consecutively, one after the other. And I'll show you what that looks like as well. Then the first thing that the exception handler does is it saves the current execution state in basically whatever the saved program status register is. It saves the entire program status in a particular register called the saved program status register. That's SPSR. Now, I'm not specifically referring to exception levels. I'll tell you what that is, because that's just one more addition to exception handling. And then you also save, first you save the state, then you save the return address in another register called the exception link register. And then you simply go ahead and, just jump to a particular handler to handle that exception however you want to. And basis that, either you panic, halt, or you skip that instruction that's actually caused the exception, move forward, whatever you want to do, you can actually implement your own exception handler. So the basic process is, an exception occurs, we look at the address in the vector-based address register, then we start saving the program status, we push the return address to the exception link register, and then we start handling the exception, right? So there's all details over here, and then there's also the ARMv8 architecture reference manual. I've been through that manual. It is very, it's very useful, because when you implement, you'll only have a few pieces. When you look at the assembly instructions that I'm going to talk about, you may not clearly understand why we're doing what we're doing, but the ARMv8-A architecture manual is very exhaustive, actually. I like it. It goes through a lot of details. So I do recommend reading those pages that I mentioned, 1874 to 1876, right? So that is at a very high level how exception handling in ARMv8-A takes place. Any questions on that? I'll show you, what it sort of looks like. All right. We'll talk about exactly how that happens in Rust with our examples. Okay. We'll exactly talk about that. So if you see, the way this works is, I told you that everything starts with the vector-based address register. So in my case, the vector-based address register is this particular symbol. It's called, I'm just calling it __ exception vector start. I'm giving it a very verbose name because, yeah, I'd like to be able to debug things. That's why. But there's some important things. This, whenever you actually say, okay, this is going to be my vector-based address register, that is, this is the address that I'm going to lay it out. All my handlers are, all my handlers are going to be located here. It has to be aligned. That means there are some particular alignment requirements. It has to be aligned to a 2048 bit alignment. Basically, it needs to be 2 KB aligned. And each exception handler, I told you that there can be 16 exception handlers. Each of them can only be about 128 bytes or hex 80 bytes. That's the point. And that's why I mentioned that they're not very similar to something like Cortex-M, where you just have a bunch of function pointers, and then, that pointer actually takes you to the handler. No, that's because the design over there is keeping in mind constraints on size, etc. Here, that's not the constraint, because we don't really have size constraints. But we want to be very efficient and fast. And that's why you actually get about 128 bytes to define your exception handling logic. But you can't, really speaking, you can't write an exception handler the way you want it in 128 bytes. What happens is, you write what is called a proxy. You can think of it that way. So the first things that you do is, that's what happens over here. This is the first exception handler, which is located at 000 from the start of this particular symbol. Here, you say that save context handle is my exception handler, and this is the particular exception level that I have not yet talked about. But let's look at save context and handle exception. If you see this is actually a macro. Save context and handle exception is a macro. We've implemented the macro over here. Basically, think of it as a function. This is the name of the macro, and this is the argument that it takes. This particular macro does nothing. At the point of the exception, whenever the exception occurs, it's basically capturing the entire program state, which means all of the registers. All of the general purpose registers are captured. Then you capture the 3 most important things, which are the program status, the link register, and what is called the exception syndrome register. Now that's very useful because that's going to tell us what exception actually occurred when we decode it. And then once that is done, you set the stack pointer, and then you simply jump to the handler. So when I move whatever, so what's happening over here is this register, which is x0, is the first argument for the function called through handler. So you remember, right? If, the way you pass arguments to functions is you push them onto the stack, right? That's exactly what we're doing over here. We're pushing all of this saved context is actually pushed on, is anyway being stored on the stack. And then we are pushing the final register that was pushed onto the stack as the argument to the handler that we're going to be calling. Okay, so here's what's happening. Let me recap this again. We jump to this location, which is exception vector start. And then that's basically going to tell us, okay, depending on which exception, it's going to invoke one of these. And whichever one it invokes, we will be able to go ahead and call the respective handler for that. This handler is something that we define, and it's not part of this, you can say this vector table. You define this separately because you don't want to be constrained by those 128 bytes, right? Does that make sense? Let me just take a pause. I hope that's making sense so far. Whatever you see here, I hope that makes sense. So basically, an exception occurs, you go look at the vector base address register, then depending on that, depending on which offset, what kind of exception what kind of exception we got, we basically go to that location and say, okay, save context and call this handler. That's all that's happening, right? That's fairly straightforward, right? Any questions on this? Okay. I guess not. All right. Cool. So you get the exception, you jump to the vector base address register, then depending on what exception what exception we got, we jump to that particular offset and then basically save the context and call our handler. Now, where are these handlers actually implemented? That's where I bring Rust in. We can actually do them in Rust. So here is where the exception handlers are. You can see this is the one that I'm going to be demonstrating anyway. So my current ELX synchronous exception is here. All it does right now is doesn't do much. It just calls another exception. It calls a handler called the default exception handler, passes some context to it, and then it just prints and panics. That's it. It doesn't do much. It doesn't sort of handle the exception and then continue program execution. No. Whenever we get an exception, this particular implementation will just record, or rather show us, print out what happened, and so that we can sort of look at it and resolve the problem. Okay, so I'll show you an example of what this looks like. I'll just need to connect my terminal, my board, and its console. Let me do that. So, yeah. So that's, everybody gets this part. There's a lot of stuff in here, about what this exception context is, all of that. This exception context is nothing but, because we're going to be printing, we want to actually print it properly. That means when we're debugging this stuff, we would like to know which bit means what in the exception. So we basically define an exception context and we say, okay, the first 30 entries are the general purpose registers. There's a link register, there's the EL exception link register, there's the save program register, and then the exception syndrome register. These are the registers that we capture and then we print them out. That's all we're doing over here. Nothing much. Right? Cool. Any questions so far? Okay. Can you guys hear me? Can you guys hear me? Just want to check. Everything looks all right. Okay, right. I just just want to double check that. Thank you, Shafali. All right. So we got this. We figured out, at least we understand the basic flow of how exceptions are triggered or rather caused and what happens once they are caused, right? Think about a scenario where, we have a program, it's executing, it hits a point where, we basically attempt a data access from a completely non-existent memory address. That means that a memory address does not exist in the memory map for that device. Okay, what are we supposed to do? Exception handling comes into the picture and says, okay, this does not exist, and we're going to go ahead and run through our exception handlers and tell you that this is what has happened. So I'll show you that demonstration now with a couple of. So I've actually written some code that's actually going to access an out of bounds memory address, and when it does that, it's going to go ahead and trigger the exception handling logic that we've just written. So you'll get to see this in action. Let me try and show you that. But before I do that, let me explain to you what that looks like. So in ARMv8-A, if I go into bootloaders, where the hardware abstraction layer that you just saw that's imported by the bootloader, and then we build the bootloader. So, but pretty much in the bootloader, you have a main.rs, which is the actual bootloader. We do a lot of things over here. All of this is not important. What we need to do is we need to basically go ahead and run this, which is I've just uncommented these 3 lines. If you see, I clearly say for this particular board, let me show you what actually happens. So if you go through the reference manual of this board and you look at its memory layout, you will see that where is give me a minute, let me just search for this. Okay, I think I have a better way of doing this. Yeah. Okay, I actually remember this, so that's why I type those addresses out. But anyway, so in our case, when you actually look at the memory space, or rather the memory map, right now, for this particular board, which is the ARMv8-A nano board that I'm using, it we don't have access to the DRAM memory yet because we have not initialized it. We will need to initialize it. So for now, the only memory that we have is this stuff. We basically have some memory that's not accessible to us from 0 to about 3 FFF, which is completely taken up by the boot ROM code. We don't have access to it. And then there is something called the internal RAM. So this is the internal ROM, this is the internal RAM. And the internal RAM is addressed from X 9000 something to 97 FFF. Okay. So I'm going to be addressing, if you look at this, I'm going to be accessing something that's out of that, out of bound, not part of this memory map. I only have access to this. I'm going to access just 1 byte outside of this. Technically, that's a non-existent on-chip RAM address. When I try to access something like that, that should trigger the exception handling logic that I have written. And that should go ahead and effectively, if everything goes right, you should be able to see the exception handling logic trigger and the debug output, right? So let me actually run through that first. I'm going to compile this, or rather recompile this, and then I'm going to reset my terminal. Before I do that, dump all of this in there. Connected my IMX8 MN Nano board to my laptop here. So let me go ahead and do that. So yeah, now it's connected. I have the console ready, compiled it. Now I need to actually sort of program the board. The way I'm doing that is I have the FTDI chip, which is the debugger that I'm using right now. I'm just going to go ahead and sort of do that, for which I will need Linux. Okay. All right. So let me get this started. So the way I'm going to do this is I'm going to just spin up OpenOCD. And oh yeah, sort of, there's an extra step. Yeah, now I'm connected to the board and I'm going to spin up GDB and basically program my board. These steps are something that we've been through a couple of times now, because we have been, okay, what happened? The connection is closed. Why? Okay, let's try this again. Oh, sorry. I should be, because I have two versions of OpenOCD. Yeah, I've been doing some debugging, so I ran into quite a few. What do you say? I had to do a couple of installations, etc., etc. I have like 2 versions of OpenOCD installed, just for my benefit. Anyway, so let me run this. Yeah, now I'm connected. And now let me just quit out the old one. I hope the font size is good enough for this. Happening. For some reason. Let me try this again. Okay. Hopefully this should work. Yeah. Okay. So I'm just going to reset the board, do all of the setup that I normally have to do. This stuff is all We've been through this. Hey. Oh. Okay. Looks like there's an issue with my okay, but in any case, it should still load, right? Okay, I think I messed up with my versions. Some reason it's not picking it up. Anyway, I've got backup exactly for this reason. Always have your backups. So when you do this, when you actually go ahead and uncomment these 3 lines, what's supposed to happen is, just give me 1 minute. Yeah, so when you actually go ahead and uncomment these 3 lines, we are supposed to get some kind of output. Let me show you what that output is going to look like. I've actually been working with the NXP team, sort of help me with, other things. So what happens is when you actually run those, when you go ahead and run the command, program the board and get it to basically run your bootloader. Right now, there's some problem with my USDHC driver that I have, which is what I'm working with. But when you do that, here's what happens. Here's the output that you're supposed to get. We start off, we start off printing well, everything's good. And then forget about all this stuff. We've sort of done other streams on this. But the important thing is, here's what happens. We try to read from this non-existent memory, and that's where the entire execution panics, because that's how we've written it now. It panics and it says, okay, there's a CPU exception. The exception has, so exceptions are divided further into exception classes in NXP, or rather in ARMv8-A. So each exception class is a particular kind, or a particular, basically is a class. And then you go look up that exception class, and then you determine what, okay, this exception class, this particular, what is called ISS, then you start deciphering what that exception really is. So for example, let me give you an example. In this case, when we're trying to read from the non-existent on-chip RAM, we got this particular exception. This is what the ESR register is for, the exception syndrome register. So if you actually decode this value, you'll be able to get an exception class of 25. If you want to understand what that is, you go look at the ARM documentation for this. And the ARM documentation is pretty exhaustive. If we actually go here, you'll be able to see that, yeah, you'll be able to see, yeah, you have all the exception classes over here. If I want to actually go look at my exception class, I have to decode what hex 25 is in binary. Hex 25 is 100101, because that's what I have here. So if I was to look at 100101, I will need to scroll down a bit, Yeah, this one, right? This is the exception that occurred. I hope everyone can see this. Can you guys see this? Yeah, this I should be free. So you've got you got the exception class. It basically says this is an exception. This is basically a data abort. In other words, we tried to access a particular memory address for some data, and there was no change in exception level. And basically that was an incorrect access. That's what it's trying to say. Now, if you want to further dive down into which parts are an exception, then you can click on this and jump to that part. And then you have more information over here, which is here about the data abort. This is the instruction specific syndrome part that you need to decode. So in the register that you saw previously, which This was the exception syndrome register. This register, the first 3 bytes are what make up the ISS. You look at that and you figure out, okay, I know the exception class. Now I need to know what particularly caused this exception. You can get there. Then there's also other information about something called FAR and SPSR. FAR is the fault address register. You can clearly see the fault address is this, which is what we're trying to access, which is an invalid address. It doesn't exist, right? And because I wrote the exception handler to print out everything, it also prints out at the point in time where the exception was taken, the current state of the program. All right. So this is an example of what you can do with, how you can actually manage exceptions in ARMv8-A. Okay. Yeah. So I quickly wanted to cover these aspects and sort of turn this into a small little session. So yeah, that's about what I wanted to cover actually. The rest of the details of the implementation is to how it's actually laid out. As I said, the entire implementation or exception handling logic is located in the HAL folder. If you go to the NXP IMX8 section and look at the exception, module, you'll find all of the exception related stuff in there, right? We start off as an assembly in assembly world, then we move to the Rust world, and then the other important piece is where you set the exception. How you set the base address, vector base address register is through this particular routine, where I actually call handling initialize, and then I specifically set the vector base address register. Now, before I actually wrap up, there's one thing that I did not cover so far, and that's a good reason, because exception levels plus exception handling generally tends to be a little complicated. Let's go back to the documentation that was put together. You will see that if you see this, the 4 different types of exceptions are listed here, and then each of the offsets are also listed here. What are these offsets? These offsets are specifically talking about exception levels. Means, apart from just handling the exception, it's also important to understand at what exception level I am. Loosely speaking, you can think about exception level as privilege levels. Okay, ARM does not use that word. They don't use privilege levels, but for us to understand, you can just call them privilege levels. Okay, basically there are about 4 privilege levels. That's EL0, 1, 2, and 3. 3 is the highest, and our code is actually running at 3, EL3, because if you actually see, I sort of print this out as well. Current privilege level is EL3. Okay, and that's why we are setting the VBAR EL3 and not the others, right? So if you actually go and look at this particular table, you will see that we have, for those different exception levels, you have different offsets, and those different those handlers at those different offsets will fire based on which level are we operating on and where the exception occurred or was caused. One key point to note is that when an exception occurs, it can only be handled at that level or a level higher, nothing lower. You cannot go lower to a lower exception level to handle an exception. Okay, that's part of the ARMv8-A rule set. And then there's also a bunch of other rules over here that you can probably read in the ARMv8 architecture reference manual. All right. Yeah, I expected to complete this in 30 minutes, but I guess 15 minutes are always supposed to be added because of technical. I wanted to show you the demo, but anyway, I have the backup for it. So I was messing around with some of the OpenOCD installations, and I think I messed it up. So I have to completely rework probably reinstall it, or maybe have a fresh install of Ubuntu. I don't know. Figure it out. Anyway, that's pretty much what I wanted to cover. So, any questions before we wrap? Okay. So I hope I was not like rushing it through because I wanted to stick to my deadline. But I hope it was useful though. And yeah, that's it from my end. And I hope you guys have a great weekend. I'll see you on the next stream then. Thank you. Good day.